So let's try this one. Radioactive carbon-14 has a half-life of about 5,730 years. We want to find the decay constant. We want to find lambda. All right, so carbon-14 is radioactive. It's undergoing radioactive decay. So let's start with our exponential decay formula. And just get in the habit. We're talking about exponential growth decay. Just start right with the equation. And we want to find the decay constant, so we know we're going to use this lambda version where we really emphasize here that the exponent is negative, so negative lambda times t. And that's multiplied. So the whole decay formula here is our population at time t is equal to our starting population, P0, times this exponential term, e raised to the negative lambda times t. And what other information we're given? We're given information about the half-life. So we're told that our population, or the amount of radioactive material at time 5,730, so that's what this value is, should be 1/2 of however much we started with. All right, so we want to find lambda. We have our formula for P of t, and we know that P evaluated at 5,730 should be 1/2 our starting population. So we can set these two equations equal, well, we can set these two quantities equal to each other, and that'll give us an equation that we can then use to solve for lambda. So let's start with this quantity that we're interested in, P evaluated at 5,730. Let's actually plug that into here. So we'll have our initial population times e raised to the negative lambda. And negative lambda is what we're trying to find. And then we're plugging in 5,730 in for our time here. And we know that if we evaluate this, it should be equal to 1/2 times our starting population. And what this does is this gives us an equation then that we can then use to solve for lambda. And kind of the same setup that we did in the last example, we have this unknown constant that we want to solve for. We want to solve for lambda. And so you just kind of have to unravel this left-hand side, this exponential equation. So you start with this constant in front, get it out of there, move it to the other side. And so if we divide both sides of this equation by P0, it's just going to cancel out. So again, that decay constant really doesn't matter. It doesn't depend on the starting size because it just ends up canceling out. So whether you start with 10 milligrams or whether you start with 1,000 milligrams, the decay constant is going to be the same for both of those materials. So if we do that, we get e raised to the negative lambda times 5,730 is equal to 1/2. Leave some spaces because we know what we're going to do. We want to get rid of this e now. So how do we do it? Apply natural log to both sides. Natural log and e just cancel out. And that gives us negative lambda times 5,730 is equal to the natural log of 1/2. And then solve for lambda. So divide both sides by negative 5,730. So we get natural log 1/2 over negative 5,730. And if we really wanted to, we could simplify this down. So this natural log 1/2 actually does simplify. So natural log 1/2, if we remember back, we learned some natural log properties. So when we have a fraction inside the log function, this gets converted into subtraction. So it's actually natural log 1 minus natural log 2, and natural log 1 is just 0. So this is actually equal to negative natural log 2. So if we fill that in, we get another way to think of this constant. So we'd end up with a negative natural log 2 up here, and it would cancel with the negative down here. So we end up with just natural log 2 divided by 5,730. So that's the decay constant for carbon-14. All right. So we're going to use this for our next topic, and that is radiocarbon dating. So we'll talk a little bit about that next. So we can use carbon-14 to kind of date organic matter in some way, how long it's been around. And we can use that then to kind of date all sorts of things. So we'll take an example. We'll take a look at an example coming up. So we'll see you there.